This presentation is about assessing normality of interval and ratio level data. There are three approaches to assessing normality: numeric, visual, and statistical. Using the numeric approach, you're going to compute a descriptive statistics table, and you're going to present the mean, median, and mode, along with skewness, kurtosis, and standard deviation, and the sample size. I call your attention to this formula here, which is the formula for a normal curve. And I've highlighted the variance, which is right here, the mean, and the standard deviation. Formulas or statistical techniques, rather, such as the F-test in ANOVA or the T-test, the Z-test, and other statistical techniques that assume normality, you'll see that the mean and the standard deviation and variance are part of that normal curve formula. So if the mean is not a good representation of the central tendency of that distribution, then this formula for the normal curve will not fit the distribution, and therefore inferences that you make as a result of a statistical test may not be an accurate reflection of what's going on in the population. In a theoretical normal distribution, the mean, median, and mode are on top of each other. As a distribution becomes more skewed, and you notice that there is a tail on either the right side or the left side of the distribution, as a distribution becomes more skewed, the mean is pulled in the direction of the skew. And the reason for that is because the mean is sensitive to outliers. Symmetry is assessed using the skewness and kurtosis statistics, and we'll go into a method of calculating those in just a moment. But kurtosis really doesn't have a large impact on the symmetry of a distribution, but it should be related to the average spread of the distribution. So if you have a high kurtosis statistic value, then you'll probably have a correspondingly smaller average spread of the distribution, or the standard deviation. The visual approach includes some visual components such as the stem and leaf plot, the QQ plot, and a histogram. And then finally, the statistical approach uses the sample distribution and superimposes a theoretical normal curve. And it's asking the question, to what extent does the sample data fit within a theoretical normal distribution? So we're going to go through an example using these three approaches in a little bit more detail. So there are some assumptions that are aligned with assessing normality. And one is that this only works for interval and ratio levels of measurement. So you can see here there are four different types of levels of measurements. There's nominal data, ordinal level data, interval, and ratio. So for this presentation, we're only going to be concerned with interval and ratio level data. I do want to call out that things like frequency counts, numbers of things, and similar types of data are nominal levels of measurement. They're not interval or ratio. Therefore, you can't use nominal level data with statistical techniques that assume a normal distribution. We have non-parametric tests that will work for statistical tests that do not assume a normal distribution. We also must assume that the sample is a random sample from a known population. Now, this has everything to do with the method of how the data were collected. And this isn't something that we can adjust um, to make it right. There are no tricks or alternative processes that once you have collected the data that you can make it a random sample. That's part of the procedures for collecting the data. I will demonstrate a process when an assumption of normality is violated about how we can do some data transformations and what that looks like. And then the final assumption is that whatever you're measuring, that it is a valid and reliable measure. So you can see in this diagram here, in this first bullseye, that you have all the points that are clustered tightly, but they're not clustered in the center. So these are reliable data, but they're not valid. In this diagram, you have a shotgun appearance where all the data are scattered around and they don't cluster in any particular area. So these type of data in terms of being valid and reliable, it's low validity and low reliability. In this type, it's not really a shotgun approach. The points are not clustered, except they are above the horizon, so to speak. So we could say that these data are neither reliable or valid. What we're looking for here in terms of valid and reliable data is that the data or the measures will consistently anytime that you're using them or in a statistical test or you're resampling, that the data are going to be consistent. The means are going to cluster around a very narrow area, and that they're going to be directed right in the center, like in this diagram, to suggest that both the data are reliable because they're clustering closely, and they're valid because all the data are clustered inside of that bullseye. These are just conceptual understandings of validity and reliability, and really for the purpose of this course you can make assumptions that the data are valid and reliable measures, even though they may not be, because you're just learning about statistics. And also we will assume that all the data were collected using a simple random sample or random selection process. So let's go into these aspects a little bit with a little bit more detail. And as I mentioned earlier, in the numerical, you're going to look at the relative position of the mean, median, and mode. And what you may observe is that in a skewed distribution, that mean is going to be pulled in the direction of the skew. So the way that you describe skewness is in terms of skew being positive or skew being negative. And you'll always know which way it is because the tail will point in the direction of the skew. So if it's pointing in the positive direction, that's a positive skew. And if it's pointing in the negative direction, that's a negative skew. And then you'll see that relative position of the mean, median, and mode. The variability, you'll want to compute the standard deviation. I don't think it's necessary to compute the variance. Those are essentially the same metric. It's just that we take the square root of the variance to get the standard deviation, and it's a little easier to conceptualize a standard deviation because the values are considerably smaller. And then we have what's called the coefficient of variation. And all that is the mean divided by the standard deviation. And it tells you what percent of the variability is related to the mean. And I'll go into an example of that in just a moment. And then finally, with symmetry, we had already talked a little bit about skewness and kurtosis, and those are all parts of the StatCrunch module, and you'll see some screenshots about some results that we're going to use on some hypothetical data here in just a minute. So let's take a look at the visual components. And earlier we talked about numeric, looking at the relative position of the mean, median, and mode. And in this diagram here, you can see that there's a slight positive skew, and in fact that mean is slightly pulled towards the positive end. In the second distribution, it's significantly skewed, and you can see how far the mean has been pulled in the direction of the skew. Here are some examples of positive and negatively skewed distributions, and also a picture or a histogram of a bimodal distribution. So one of the interesting aspects of creating these histograms is in terms of what's called binning, B-I-N-N-I-N-G, and it has to do with the number of columns, the number of slices that you're going to have in these data to compute some frequencies at particular points. If the number of bins is too small, then you may not be able to see bimodality. Whereas if the number of bins is too large, then you may not be able to see anything. So what is the right number of bins? Well, a good rule of thumb is between 8 and 12 bins, depending on the spread of the data. I think that StatCrunch will default and will compute whatever it believes is the best representation of the data. There are some statistical applications, and there are theories behind the number of bins that are appropriate for certain kinds of distributions, but we're not going to get into that in this course. And then here you can see the metric of kurtosis and leptokurtic. The visual there is you can leap over it, mesokurtic or median or moderately, and then platykurtic or a plateau or a flattened distribution. And then we have the statistical test. And basically what these tests do is to create a normal curve given this formula that I have right at the bottom here. And it will compute a theoretical normal curve given a particular mean and standard deviation for that distribution. And then it will superimpose the actual data, the histogram of the data, onto a normal curve, and it's going to compute the differences between the normal curve and the data. And what I have up here at the top is just a conceptual formula, and what I'm trying to convey here is that if you just sum the deviations in green and the deviations in red, those are going to sum to 0. And that's why you need to sum the squared deviations, and then that will not sum to 0. And that's kind of essentially what the Shapiro-Wilk formula is doing, which is the W statistic. And here is an example of what that formula looks like. You don't need to know the formula, and you don't need to know how to compute it, because StatCrunch is going to do that for you. What you do need to know is how to interpret it, and we're going to go into an interpretation of all of these in just a moment. I think that using the Shapiro-Wilk test is preferred in this course because it's asking the question, was the sample selected from a normally distributed population? I will say that the shape of the population isn't really all that important. I think we're sometimes a little more concerned with the shape of the sample, but there are too many other components of the Anderson-Darling assessment of normality that go beyond the expectations of this course. So let's just keep it simple and use the Shapiro-Wilk, and I'll tell you how to interpret those outcomes in just a moment here. So let's take a look at the data. These are the data in the file that I created. I just made up numbers. They don't really mean anything. You'll see that the data consists of 28 scores, and here are their values, the frequency in which they occur. So there's one value of 12, one value of 14, one value of 15, and so forth. And then I correspond these frequencies to what you're seeing here in a histogram. It's an ungrouped frequency histogram for this distribution. So you also want to look at the 50th percentile, which is called Q2. Q1 is the 25th percentile, and Q3 is the 75th percentile. And what I want to look at here is Q2 in the middle of the distribution? And it appears to be. So that gives me some insight. I also see that there are a lot of unique values. There are only 3 values, 18, 20, and 45, that have multiple frequencies, frequencies more than one. So my observation here is that these are mostly unique values, which is fine. The median appears to be centrally located. That's good. Don't really know if it's a random sample, but we'll assume so. Let's take a deeper dive into the numeric qualities of the distribution. And again, we're looking at central tendency, variability, and symmetry. So what are we seeing here? 39.25 and 28.50. So clearly we can see that the mean, which is in green right here, is pulled into the direction of the skew. So the mean is affected by outliers, and we can see that the mean is larger than the median. So we kind of tuck that little piece of information away. Now then, let's take a look at the standard deviation and variance of the sample. And we really don't need to interpret that directly, because there's no relative positions of that. However, there are 2 formulas for computing the standard deviation and variance. And you need to know this in StatCrunch, because it will ask you, are you wanting to use pooled variances, or do you want to use unique variances or unpooled variances? And so how do you know? Well, I would say that in the not pooled variances, that would actually be in a statistical test such as a t-test or ANOVA. The population variance is the unadjusted variance. And from your readings, you know that the formula for the variance of a population has n as the term, whereas in the formula for the standard deviation and variance of the sample, it's n minus 1. And they use n minus 1 to reduce the variance, reduce the bias from small sample sizes. So, as the sample approaches the size of the population, then you're going to see that some interesting things occur in terms of your sampling error and some other things. But keep in mind that we use inferential statistics so that we don't have to gather all of the population data, because sometimes the population data is inaccessible. So we assume that it's there. We make some assumptions about the population, but we take a random sample from it. And then another assessment of variability is called the coefficient of variation. And in this value, you see that the CV is 71.06. And this means that the standard deviation is 71% of the value of the mean. Now, that may not make too much sense right now, but later on I'm going to show you what happens after we do a transformation that will kind of shore these data up and make it better conform to a normal distribution. And then finally, in terms of the numeric aspects of symmetry, we're going to look at skewness and kurtosis. Now, the book does give you some rules of thumb about how to assess skewness and kurtosis, and I think generally speaking, if they're above +1 or below -1, then those are indicators of skewness and kurtosis. A better way is to compute the standard error of skewness and the standard error of kurtosis, and then take the ratio, the skewness statistic divided by its standard error and the kurtosis statistic divided by its standard error. And you'll see in the PDF, it doesn't come across very clearly here, but I have those formulas for the standard errors of skewness and kurtosis. And this makes it really easy to interpret, because if these ratios are greater than 1.96, and 1.96 should ring a bell for everyone about now. That's the z-score associated with 5% under the curve. If those values are greater than 1.96, or you can kind of round it up to 2, then you know that there are some significant problems with skewness or symmetry in these distributions. So what do we see here? We see that the mean is larger than the median, that the standard deviation is 71% of the mean, and that the skewness and kurtosis ratios are greater than 1.96. So right off, we know that there are some problems with this distribution as compared to a theoretical normal distribution. So let's talk a little bit about the standard error, and this isn't something that you're going to cover in Module 3. It comes into play, I think, in Modules 5 or greater, but it is something that is an important concept for you to know right now. So let's take a hypothetical example, and let's say that I have a jar of marbles. 50 of them are white, and 50 of them are red. Now, let's say that I take a sample from it, and really it doesn't matter how big a sample size that I take, because the central limits theorem will tell us that the mean of the sampling distribution is by definition the mean of the population. So let's take an easy sample, a sample size of 10. So I have 100 marbles in there. Half of them are red, half of them are white. And I shake the jar up real good, randomize it, close my eyes, scoop my hand in there, and grab 10 marbles. Now, will I every time get 5 red and 5 white marbles? No, I won't. I'm sometimes going to get 6 and 4, 7 and 3, 3 and 7, 4 and 6, 1 and 9. It's all over the map. So that doesn't really concern me, provided you take a random sample. But you also have to have a reasonably large sample size. So let's say that rather than taking a sample size of 10, that I take a sample size of 98. Now, there is a different kind of sample, because the sample size itself is nearly the size of the population. And there are only 2 outcomes. Either I'm going to have, or 3 outcomes. I'm either going to have 2 white marbles left, 2 red marbles left, or 1 red and 1 white marble left. But my sample size is going to contain 98 marbles, half are red and half are white. So I have a sample that really reflects the characteristics of the population. So let's take a look at this formula for the standard error of the mean. You see that it's the standard deviation of the sample divided by the square root of the sample. So as that sample size gets large, as it grows to infinity, then that standard error, that quotient right there, uh, goes to the size of the standard deviation of the mean, or the standard deviation of the sample. So what we see is that the sampling error, which is aka the standard error goes to zero as the sample size approaches the population size. But when you have a small sample, 10 or 20 or 30, and you have an infinitely large population, then the standard error is something that we need to contend with. And it becomes a very large topic in some of the statistical tests that we're going to study in upcoming modules. So keep that kind of tucked away, and you may want to come back to this slide or this portion of the presentation when we start covering t-tests and ANOVA and things like that that require a computation of standard error. And there are standard errors for all kinds of statistics. It's not limited to just the standard error of the mean. We can have standard errors around regression coefficients and things like that. You'll see standard error coming up, and it has everything to do with the ratio of the standard deviation to the square root of the sample size. In this chart right here, what I'm doing is depicting as the sample size grows large, then the 95% confidence interval, the standard error, goes small and eventually approaches zero. So you can see that the curve takes a fairly sharp turn right at the very beginning, and you can see that for very small sample sizes the standard error is really large, and then for large sample sizes the standard error is relatively small. So as the sample size approaches the population size, and it does so exponentially, once the sample size approaches or is equal to the population size, the sampling error is zero. So now let's turn to the visual components, and I'll begin with the stem and leaf plot, and I'll show you how to interpret this. The interesting thing about a stem and leaf plot is that you are using the data, the actual data from your data file, in generating a visual representation. So in this first row here, you have 1 colon 2 4. So this means you have a value of 12 and a value of 14. In the second column, you have 1 colon 5 6 6 8. So you have 15, 16, 18, and 18. And that's how you interpret a stem and leaf plot. You can also see from the stem and leaf plot that it's highly positively skewed. So now let's look at the quantile, or otherwise known as the QQ plot. And it is no different than a histogram. It's just a different way of showing it. And what I've done here is to map correspondence from the QQ plot onto the histogram. So let's take this little point right there that is at what, about 10 and about 2.2. Well, that corresponds to this area right here, and you can see that these points here are underneath the theoretical normal curve line, and that's what this line is right here. So you don't talk about linear relationships when you're describing the quantile plot, even though it may kind of look like a scatter plot. It's not. So in your interpretation of normality, and you're interpreting the QQ plot, you will not talk about the data look like that it's linear related. Well, because linear related to what? And you can see where the raw data cross the line of the theoretical normal distribution. You can see over here in the histogram, that's when the data at 0 cross the theoretical normal curve line. And similarly, if you look up here on the QQ plot, that's the point that crosses the theoretical normal curve, and that's what corresponds to the histogram. So you have the stem and leaf, the QQ plot, and the histogram. Now let's turn to the statistical. And recall that I said that the way that they do this conceptually is to take the raw data and compute a frequency distribution and then superimpose a normal curve and then calculate the deviations from the sample to the normal curve. And I've indicated the positive deviations in red and the negative deviations in green. And if you sum those up, they're going to sum to 0. And that's why you have to compute the squared deviations about the mean. So you'll hear this term, this phrase, the sum of the squared deviations about the mean. That's used to describe how you would compute the variance or standard deviation. It also describes many other kinds of concepts in statistics. So let's look at how you would go about interpreting the Shapiro-Wilk test. One of the things you're going to need to memorize, and if you don't want to memorize it, then write it down on a sticky note and paste it onto your computer monitor. And it goes like this. If the p-value is greater than or equal to 0.05, decide retain the null hypothesis. Conclude no difference. If the p-value is less than 0.05, decide to reject the null hypothesis and conclude significant difference or significant relationship, depending on what it is. And in this case, the way that you would interpret this is that according to the Shapiro-Wilk test, the sample distribution is significantly different from a theoretical distribution with the same mean and variance. Finally, after you have gathered all of your data and performed all of the statistical analyses, you're going to need to pull all of this together. You're going to need to synthesize all of these outcomes, because you can't just present the data and then let the reader, who in this case is going to be me, to figure out what it all means. You need to tell me what it all means. And the way that you go about doing this at this step is to write a brief discussion of the synthesis of your results. So you're going to take the numerical. Well, there was a positive skew, and the skewness was statistically significant because the skewness statistic of 1.78, which is greater than 1, was also had a z-score of 4.81, which is greater than 1.96. So we have evidence of a significant skew that is statistically significant. In our visual analysis, we can see from the histogram that it has a positive skew, and we can see the relative position of the mean and median. And then we also look at the statistical outcomes, and there was a significant p-value here, and therefore the sample distribution was significantly different from a theoretical normal distribution that has the same mean and variance. Also, you want to take into consideration the sample size, and an N of 28 is probably a decent sample size, and I think module 7 or so you're going to compute a power analysis, and that's going to let you know how big a sample you're going to need to take. Well, one of the unknowns is, was this a true random sample? D and K, do not know, and it's unlikely, but we can't fix that. You'll have to just maybe comment that there could be sample bias, and urge caution about generalizing to a fairly narrow population. Evaluation. This is the final component of assessing normality. And basically, it's asking the question, given your synthesis of statistical outcomes, to what extent is the sample mean generalizable to the parent population? To what extent is the variable ready for inferential analysis? So, if you believe that the distribution is significantly skewed and there are a lot of problems with it, in this course, all you need to do is just call it out. You don't need to do anything else with it. But I do want you to recognize it and call it out when you see it. In more advanced courses in statistics, you'd be able to compute a transformation that will help normalize the shape of the distribution. So in moderately positively skewed distributions, you can take a square root of each of the values. In substantively positive skewed distribution, you can take the log base 10 of each of the data points. And then if there are zero values, then you can take the log base 10 of each point plus a constant, and the constant is the difference between the lowest value and zero. So if the lowest value in your distribution was 7, then the constant would be 7. That's what you would add to it, because you can't take a logarithm of 0. There are some good information about doing transformations in Tabachnik and Fidel. It's a great multivariate statistics book. So I kind of run through a little example here. This is the distribution that we were dealing with in the beginning of this presentation. And these are all of the results that we covered. Now then, what I did was to compute a log base 10 of each score and then recompute all of the descriptive statistics. Now, the means and medians, these are in logarithms. So what you would need to do is to take the anti-log of the mean and the anti-log of the median when you report it. You can see in this histogram here that it looks a little bit better in terms of the spread and the skew than the original. You can also see that the coefficient of variation is significantly less. So we've reduced the size of the standard deviation, and you can see that the standard deviation here was nearly 28, and here it's much less than 1. And then the coefficient of variation is 17%. So only 17% of the standard deviation is the mean. And so I think we've helped this distribution a lot. Also, when I computed the Shapiro-Wilk test, that it was now not significant. So the competency assessment. How do I evaluate your work? I think in terms of writing up your analysis, and of course you know that I use a rubric, and I would urge everyone to read those rubrics very carefully before you submit your homework, because there may be nuances that aren't covered or called out in the assignment. It may not be called out explicitly in the assignment template. So I'm looking at the level of relevant detail, because if you are not discussing this, I do not have a way to gauge how much you know. So if your responses are relatively brief, you're going to get a lower score than if your responses were more significantly or sufficiently fleshed out. I want you to discuss these things. Also, the way that you communicate, your writing fluency. If grammar, syntax, spelling, word choice, coherence, and focus disrupt your ability to communicate clearly, that's going to negatively affect your overall assessment. The technical skills, calculation accuracy. You know, the good news here is that you're going to use StatCrunch. You can use SPSS, SAS, Minitab, or any other statistical packages that you may have a lot more familiarity with. That's fine. But one thing you may not use, and that's Excel. It's not okay to use Excel. And here are why. I mean, Excel, like, it does a good job of, computing averages and variances and things, but it will not compute a histogram unless you know how to write code in Excel. And Excel, even with some of the add-on packages, does not have everything that StatCrunch is going to have, such as post hoc tests and things like that. So do not use Excel. The expectation is StatCrunch. It's not that expensive. I think it's like $12 or $15 for 6 months. I gauge your understanding according to the accuracy of your interpretations, the decisions that you make, and the conclusions that you draw. And I'm also interested in the insight that you have into your work. And that's why I include in graduate courses an evaluation of statistical outcomes in context. This course, the content in this course, is identical to the content you would find in an elementary statistics course and in high school and at a community college, a sophomore level course. So how does this become a graduate level course? Well, it becomes a graduate level course by expecting graduate level work, which is critical thinking, how you're thinking about things, and that you're not making decisions unless you've done your full due diligence in terms of the full analysis and your ability to communicate that analysis. So this kind of sums up the evaluation of normality, and just to kind of reflect, those three approaches are the numeric approach, looking at really all the data, the outcomes that you have in a descriptive statistics table. You're going to use the APA table templates documents unless you have mastered APA. But if you haven't, you need to be using the APA table templates document, and you know that I've already given you a video about how to use that. If you have any questions about this, you're certainly welcome to email me, schedule a phone conference with me. I hope that this gives you some insight not only into completing assignment 3.5, but you're going to be expected to assess normality in assignment 4.2, assignment 5.3, and assignment 6.3. And if your final project uses interval or ratio level data, you will be expected to do a full evaluation of normality to assess that assumption along with all the other assumptions that underlie that particular statistical test.